Most of us don't stop to think about what's happening when our screens update. We just expect it to work. Well, a subscriber from our community wanted to know how this process actually works. And the truth is, there's nothing mysterious happening. It's just a process, a very fast and precise one. And once you see that process, the whole system finally clicks. So in today's video, we're going to be following one frame from memory all the way to your screen. Let's get started. Alright, if you're here for just the high-level summary, here it is in 30 seconds. First, your CPU and GPU work together to build a single image called a frame in a special selection of memory. Then, a part of the GPU called the scanout engine reads that finished frame and streams it out, pixel by pixel, in a perfectly timed row-by-row order. Then, that data stream is encoded and sent over your HDMI or DisplayPort cable. Finally, your monitor catches that stream, decodes it, and tells its physical pixels exactly what color to be. And that's it. Application to memory, memory to cable, cable to screen. But how? How is that frame built? How is it timed? And why does it sometimes go wrong? Well, that's what we're going to take a look here into a deeper dive. To understand the journey, you first have to meet the key players. Think of this whole process like a high-tech factory. We first have the CPU and your application. This is the director. It decides what needs to be drawn. It's the boss that says, the player just moved and we need a brand new frame. Draw the character over there. Next, you have two kinds of memory. System RAM and VRAM. Think of System RAM as the factory's main warehouse. It holds all the application data, game assets, and a to-do list for the CPU. VRAM or Video RAM is the specialized ultra-fast workbench right next to the assembly line. Because it's so fast and built right into the GPU, it's where the current frame is built and stored for display. And now we have the star of our show, the GPU, or Graphics Processing Unit. The GPU is so important and actually plays two completely different roles. First, you have the render pipeline. This is the master artist, or the main factory line. It takes the abstract commands from the CPU and does the hard work of creating the 2D image. Second, you have the scanout engine. This is the delivery truck. This part of the GPU doesn't care how the image was made. Its only job is to read the finished painting at a fixed schedule and ship it out the door. That finished painting it reads is called the frame buffer. This is literally just a block of VRAM that holds the final color value for every single pixel on your screen. For a 1080p display, that's over 2 million pixels. For 4K, it's over 8 million. And finally, you have the video link, your HDMI or DisplayPort cable, and your monitor's T-Con, or timing controller. This is the final delivery and assembly line, turning that data stream back into light. And now that we've met our players, let's follow the life of one single frame. It all starts with the director, your game and CPU. The game says the player just moved forward, the CPU figures out what that means for the 3D world and sends a batch of commands to the GPU. These commands are basically draw all these 3D models at these new positions. This kicks off the render pipeline, or the master artist. First, vertex processing. The GPU looks at the 3D models, which are just big lists of 3D points called vertices. It calculates where all these points will be on your 2D screen. It then enacts something called rasterization, which is where the GPU connects the dots and fills in those 2D shapes. It converts the vector shapes into a grid of pixel candidates. It's basically creating a 2D stencil for the final image. Then the third step is it will start doing pixel shading. This is the most intensive part. Every single pixel in that stencil, the GPU runs a tiny program called a pixel shader to figure out its exact final color. This is where all the complex lighting, shadows, and textures are calculated. And then fourth, our output merger. Finally, the GPU takes that final colored pixel and writes it into the frame buffer in VRAM. And boom, in just a few milliseconds, the GPU has done this for all 8 million pixels, and we now have one complete 2D frame sitting in the VRAM workbench ready to be seen. But how does it get from the workbench to your screen without seeing all that messy painting? That's where our next character comes in, the compositor. So our GPU just painted a complete frame into the frame buffer, but in a modern OS like Windows or Mac OS, there's a problem. Your game isn't the only thing on the screen. You've got other windows, your taskbar, and maybe a transparent menu. Your GPU didn't just render the game. It's also rendered the Chrome window into their own private frame buffers. So who's responsible for combining all of these separate pictures into one final image your monitor will show? That's the job of the compositor. In Windows, this is the Desktop Window Manager, or DWM. Think of the compositor as the operating system's digital artist. Its job is to 1. Take the finished canvas from every application, 2. Stack them all together like layers in Photoshop, and 3. Handle transparency and draw your mouse cursor on top. Then 4. Flatten all these layers into one final complete desktop image. This final image is what gets sent to the next step. So if you're playing a game in full screen exclusive mode, your game gets to bypass the compositor. But for almost everything else, the compositor is the crucial middleman that builds the desktop you actually see. So now that our compositor has a final 2D frame ready to go, now we have to show it. The simplest way would be to have one frame buffer the GPU writes to, and the monitor scanout engine reads from it at the same time. This causes a huge, ugly problem called tearing. Tearing is what happens when the monitor reads the buffer while the GPU is still writing to it. The monitor ends up showing the bottom half of the old frame and the top half of the new one, creating a visible tear in the image. The solution to this is a clever technique called double buffering. Instead of one, we use two frame buffers. First, the front buffer. This is the live buffer. It's the only one in the monitor scanout engine is allowed to read from. It's the finished painting on display in the gallery. Second, the back buffer. This is the hidden buffer. It's the only one the GPU or compositor is allowed to write to. This is the new canvas the artist is secretly painting on in the back room. The GPU paints the next frame into the back buffer. All the while, the monitor is safely reading the current frame from the front buffer. Then, at one specific, perfectly safe moment, they swap. The back buffer becomes the new front buffer, and the old front buffer becomes the new back buffer. The monitor now reads the new frame, and the GPU is free to start painting the next frame onto the now hidden old front buffer. This swap is instant and happens in a tiny fraction of a second. Now that we've got our buffer system, the GPU is painting to the back, the monitor is reading from the front, but what does reading from the front actually mean? This is the absolute core of our question. It's done by the scanout engine, that delivery truck part of the GPU. The scanout engine is, well, very dumb, on purpose. It doesn't know what a game or window is. Its only job is to read the front buffer at a fixed, relentless pace, and it reads it in what's called scanline order. That means it reads the color of the first pixel in the first row, then the second, then the third, all the way across. When it hits the end of a row, it immediately jumps to the start of the next row and does it again, top to bottom, left to right. But how does the monitor know when one line ends and the next begins, or when one frame ends and the next begins? It can't just be a raw stream of pixels, it needs punctuation. This is where HSync and VSync come in. Think of the data for one frame as a page of text. The horizontal sync or HSync pulse is the punctuation at the end of each line, like a comma. It's a tiny digital signal that tells the monitor, okay, I'm done with this line, move down to the start of the next one. Then vertical sync or VSync pulse is the punctuation at the end of the entire page. It's a longer signal that tells the monitor, I'm done with this entire frame, move back to the top left corner and get ready for the next one. These little pauses between lines and between frames are called blanking intervals. Even on our modern flat panels, we still need these pauses in the data stream so that the monitor's electronics have time to lock on and prepare for the next batch of data. And that vertical blank, the longer pause between frames, is the single most important part of our timing. That critical pause, the vertical blank or VSync pulse, is the only safe moment to do our buffer swap, to tell the monitor to stop reading the old frame and start reading the new one. And this single choice, when to do the swap, is the source of all the settings like VSync, G-Sync, and FreeSync. VSync on, this is the polite option. The GPU finishes rendering a frame to the back buffer and waits for that VSync pulse. As soon as it arrives, it swaps the buffers. What's good about this is it perfectly eliminates tearing. The bad thing is stutter. If your GPU is slow and misses that pulse, the monitor is forced to display the same frame twice. You perceive this as a stutter or lag. Also, if the GPU finishes early, it just sits there waiting, which can add latency. Then we have VSync off. This is the rude option. The GPU swaps buffers the instant it's done rendering, whether the monitor is ready or not. The good thing is that there's very low latency with this, since the GPU never waits. However, the bad is this is the definition of tearing, as the monitor will almost always be caught mid-scan. We then have adaptive sync, like G-Sync or FreeSync. This is the smart solution. It's the best of both worlds. Instead of the GPU waiting for the monitor's fixed 60 Hz pulse, the GPU tells the monitor when it's finished. The GPU finishes the frame and immediately tells the monitor, okay, I'm ready. The monitor instantly generates its VSync pulse and performs the swap. The monitor's refresh rate becomes dynamic, perfectly matching the GPU's output. No tearing, no waiting, and no stutter. And now that our GPU has finished the frame and synced it up with the monitor, it now needs a way to actually get that image to your screen. That job belongs to HDMI and or DisplayPort. These protocols aren't just dumb pipes. They are active, intelligent systems for encoding, sending, and decoding that pixel stream. First, HDMI. HDMI uses a method called TMDS. Think of it as 3 lanes on a highway, one for red data, one for green, and one for blue. Then we have a 4th lane that provides a clock or heartbeat that keeps both ends in perfect sync. It's a very reliable fixed rate system. Second, we have DisplayPort. DisplayPort is more advanced and works more like your computer's internet connection. It sends the video data in tiny packets. This is more flexible. It can use 1, 2, or 4 lanes depending on the bandwidth needed. This packet system is why DisplayPort can do things like daisy chaining or running multiple monitors from a single cable. But for extremely high resolutions like 4K or 8K, the data stream is so massive that even the best cables can't handle it. So they use a new trick called DSC, or display stream compression. DSC is a visual lossless zip file for your video stream. Your GPU compresses the frame in real time. It sends the smaller data over the cable, and your monitor unzips it in real time before displaying it. It's so fast and efficient, you cannot see the difference. It's the only way we can achieve today's highest refresh rates. And so now that we have our compressed, packetized, or TMDS encoded data stream, we have finally arrived at the monitor. The journey is almost over, but the monitor itself has a few key players to finish the job. First, the EDID. The very first thing that happens, even before you see a picture, is a handshake. The moment you plug in the cable, the monitor sends a small chip's worth of data back to the GPU. Think of it as the monitor's resume. It says, "Hi, I'm a Dell monitor. I support 1440p at 165 Hz. And here are the color formats I understand." This is how your PC knows what resolutions to offer you in the settings. Next, the TCON, or timing controller. This is the brain of the monitor. It receives the raw video stream from the HDMI or DisplayPort, unzips it if its DSC was used, and uses the HSync and VSync timing pulses to perfectly rebuild the frame in its own small buffer. Its most important job is to convert the digital pixel data into the precise analog voltages that the physical panel needs. And finally, the panel drivers. This is where data becomes light. The TCON sends these voltages to the panel drivers, which are a set of chips surrounding the glass panel. A row driver selects or activates one single row of pixels on the screen. The column drivers then send the exact voltage for each subpixel, red, green, and blue, in that one row, making it light up with the correct color and brightness. The row driver then deactivates that row and reactivates the next row, and the process repeats all the way from top to bottom of the screen, 60, 144, or even 240 times every second. And with that, our frame's journey is complete. It has gone from an abstract idea to a 3D model, to a 2D pixel in VRAM, across a cable, and finally to a tiny light-emitting crystal on your screen. And there you have it, the journey of how one frame is created and is processed through your entire system to get to you. A massive thank you to the subscriber who recommended this topic. And if you would like to see your suggestion on this channel, please leave a comment below detailing what you would like to see. And if you enjoyed this video and would like to support the channel, leave a like and subscribe so you don't miss the next one. Thank you so much for watching, and as always, keep growing.